Thank you very much. It's a real pleasure to be here. I've had a lot of fun hanging out with some of you today, especially talking with some of the students. I want to tell you a bit about some of my favorite math fun facts. And to do that, I first have to tell you what a math fun fact is. So what are math fun facts? When I started teaching several years ago, my lower division courses, such as a calculus course, I would often start off with a 5-minute math fun fact, which could be just an interesting idea from many different areas of mathematics, just to show my students that math is actually pretty cool. So what are they? Well, they're ideas that often involve a change of perspective. So it'll change the way you think about something. It might generate some questions. The idea is to arouse your curiosity and fascination with math, and they should be fun. Often there's some element of surprise or that you get from hearing the fun fact. And as I mentioned, I've used them not just in classes to whet people's appetite for mathematics, but also for project ideas. So why do I do fun facts? Well, I do them just to show that math is actually more than just dealing with numbers or dealing with just learning calculus. I mean, after all, calculus is a very useful subject. And if you're a scientist, it's important to know. But you don't get to see in calculus some of the very cool and neat things that have been developed more recently than calculus. Calculus is 400 years old, right? So you sort of get a sense that it's all cut and dried and it's just about formulas if you just end your mathematical career with calculus. So I like to do that. And I also want to show my students that math is both a science and an art. It's the science of patterns and the art of meaningfully engaging with those patterns. And so hopefully you'll get some surprise, insight, or joy out of seeing some of these. And so if you're interested, I actually have collected all the fun facts, many fun facts, on a website. You can find it if you just Google math fun facts. And I started this as a hobby back when the internet was still young. If I were to do it today, I probably would be writing a blog, but it's in the form of a website, and it gets about 1 million hits a year. If you don't have internet connection and you have an iPhone, well, there's an app for that. Okay. So what I'm going to do is I'm going to show you some of my favorite fun facts. Of course, I love them all, but I'll show you some of the ones that I think you might enjoy. And along the way, I'm also going to try to trace some of the people we have to thank for some of these fun facts, some of the contributions by different groups of people. Now, why is it hard to give a talk like this? Well, one reason it's hard is that some of you know some of these fun facts already, okay? And so if that's true for you, then don't spoil the fun by shouting out the answer if you know it. Let the people who haven't seen it before enjoy the fun fact. But you can obviously play along and think along with me. So I hope you won't spoil the fun for others, okay? So let's just get started. So I'm going to start with a very simple trick I'd like you guys all to do. So I'd like you to, each of you, to pick a number. Let's say pick a number between 1 and 10. Okay? In your head, everybody done that? Yes? Okay, good. Now what I'd like you to do is to square the number, which means multiply it by itself. Yes? Have you done that? Great. Okay. And now I'd like you to, from this new quantity in your head, I'd like you to subtract your original number from this quantity. Yes? Good? Okay, great. Now, take this quantity that's in your head and divide by your original number. Everybody done that? Yes? Okay, great. And let's see. You, tell me your name. Holly. What's your favorite number? 3. I'd like everybody to add 3 to to the number that's in your head right now. Yes? Okay. Great. And let's see. What about you with the cap? Jay, what's your favorite number bigger than 10? Bigger than 10? Well, just favorite number, whatever. 15. 50. Oh, that's actually pretty big. Yeah, go ahead and add 50 to the number in your head. And blame it on him if you can't do it. Okay. Okay, has everybody should have some number in your head, yes? Okay, now what I want you to do is I want you to subtract your original number. Got that? Yes? Okay, great. So now I'm going to make a prediction that the number you're thinking of right now, and if I get it right, don't hold back your applause, is 52. Okay. So this is, I'm sure you've all, how many people have played a game like this before, maybe back when you were kids? Okay, now, to be honest, I actually didn't prepare this trick. I just made it up in my head as we went along. And I'm going to show you a trick. I'm going to show you how I did it. It's actually pretty simple. It's based on a very simple idea. It's basically based on algebra, which all of you learned in middle school. So you guys start with a number, right? Like Holly, what did you start with? 3, okay, because it's your favorite number. Great. Well, I started with another number. I called it x. Yes? Oh, that's great. I don't want to write my x's that way. I'll write it like this. I started with x, and then basically what I did is a series of operations that, by the end, eliminated the x. Just doing algebra in my head. Now, of course, I'm not doing something so simple that it's obvious what I'm doing. It would have been a stupid trick if I said, think of a number, add 3, subtract your original number. You're all thinking of 3. You wouldn't have been impressed, right? But this is what we did, and you can follow along here. X, what did I say? Square it. Then what did I say? Subtract your original number. Then what did I say? Divide by your original number. I mean, if you take x squared minus x and you divide by x, you get x minus 1. Then let's add Holly's number, which is, oh, it was 3, right? X plus 2. And then let's do Jay's trick. What did he say to add? 50? Then get x plus 52. And then we said subtract your original number, and what you ended up with was 52. Yes? Ah, nifty, right? So this is actually points out something really useful. And that is, even if you are learning something that you think is boring in some class, you can turn that around into an opportunity to be creative, right? Come up with a magic trick that uses this idea, right? And this is how a lot of these kinds of mental tricks work. Now, what did I write down here? I said thanks here. Well, what did we just use? Well, we just used algebra, like the beginnings of algebra. And one of the people that we have to thank, of course, there's been a long history of people, many cultures developing the basic ideas in algebra, but Al-Khwarizmi, who is a Persian mathematician from long ago, probably wrote what we would call the foundational book in algebra, where people start taking objects, taking equations and subtracting the same thing from both sides and manipulating them as we might do today. In fact, if you look at the name of the book, what do you see in the name of the book? Algebra. That's actually where we get algebra. So this is, we can all thank Al-Khwarizmi for algebra. All right? Great. That's the first fun fact. Let's give Al-Khwarizmi a big thank you. Actually, another cool fact is that this name, when transliterated into Latin, actually is pronounced algorithmi. So it's where we get our name algorithm, the word algorithm in computer science. Okay, great. Here's a second fun fact. What I'd like you to do is to look at these 4 quantities and try to decide which one you think is largest. Okay? So A is the number of stars in the universe. B is the number of seconds since the Big Bang. C is the number of orderings of a deck of 52 cards. And D is the number of ways to fill out an NCAA bracket. Okay? And don't calculate, just give your intuition. Okay? Don't calculate. I know some of you can figure some of these things out. Just use your intuition. Okay? Which one do you think is largest? So let's see, by a show of hands, how many people think the largest quantity here is A, B, C, D? Okay, wow, pretty evenly split, although there were actually probably fewer Ds. Right, well, let's see what the right answer is. I'm going to go from smallest to largest. The smallest here, in place number 4, is, oh yeah, I didn't even ask you what you think is smallest. So I saw what you thought was largest. Let's see, which one do you think is smallest? Show of hands. How many people think the smallest number on this list is stars, seconds, orderings, and number of ways to fill out an NCAA bracket? Oh, okay, that's even more evenly divided. Okay, the smallest quantity on this list is B, the number of seconds since the Big Bang. Yes, believe it or not. Number of seconds, so I think we estimate basically the universe is about 3.7 billion years, and in seconds it's about 10 to the 17, a little less than 10 to the 18, okay, a number that's 18 digits long. It turns out the next largest is the number of ways to fill out a bracket, and that's about the same size but a little larger. That's about 10 to the 18, just over. Okay, that's 2 to the 63, it turns out, because there's 64 teams in the tournament. Okay, and the second largest is the number of stars in the universe. That's about 10 to the 23. Really? Okay, that's a number that's 23 digits long. This is what scientists estimate. And the number of orderings of a deck of 52 cards is, of course, it's number 1. But guess what? It is a number that's basically about 10 to the 68. A number that's 68 digits long. That's so large that if for every star in the universe there was a whole nother universe of stars, that would be the square of 10 to the 23. That's still smaller than the number of ways to order a deck of 52 cards. What this also means is that if you take a deck of cards and you shuffle it, you produce another configuration, right, of deck of cards. And suppose somebody was sitting around shuffling a deck once per second since the beginning of time. You wouldn't even run through a tiny infinitesimal fraction of the number of orderings of a deck of 52 cards. You know what this means? This means that every time you shuffle a deck of cards, you're making history. That's the first time, most likely, that configuration's ever been seen in the whole history of the universe. Isn't that amazing? You are making history by card shuffling. Making history by card shuffling. Hey, that's awesome. And of course, who do we have to thank? Now, why did I say this? Why did I say this? Thank the Chinese. Who are we thanking for what? Yes, well, I think I just put that because I'm sure lots of cultures have developed playing cards, but probably the first instance that we know of are Chinese playing cards. Okay, and playing cards have actually motivated a lot of interesting mathematics because, after all, there's a lot of patterns to study, right? And so it mixes in combinatorics, probability, and just a lot of basic questions you might have fun with understanding patterns. Okay, great. That's the second fun fact. Do you like that fun fact? Was that cool? Awesome. All right, good. Great. How many people here play football? How many people watch football? Yeah, okay, great. That's good enough. Good enough. How long is a football field? It's undefined. Did somebody say it was undefined? Okay. So let's see. So a football field is 100 yards. Yes, that's true. It's 100 yards. And but let's suppose I include the end zone. So there's 2 goalposts here. Yes. So how long is it from goalpost to goalpost? 120 yards. Yes. Okay. Now, suppose I run a rope across the field so that it's tight between the the two poles, yes? Okay. And now, let's suppose that I add just 1 foot of slack. That means an extra foot. Okay, so now it's a little loose, yes? Suppose then I pull the rope up at the center, at the 50-yard line, and ask what's going on there. So now what's going to happen? The rope gets pulled up a little bit, yes? And I want to know, how high does the rope get pulled up at the center of the field? Okay, don't calculate, just use your intuition, okay? And you have 4 choices. How many people think, here are your 4 choices, that when you pull up at the center, that it'll still be pretty tight and you can barely put your fingers under? That's A. The next one is you can crawl under. That's B. Next one is you can walk under, and the last one is you can drive a truck under. Okay, so vote for one of those. Everybody vote. Okay, even if you don't, just use your gut. Okay. How many people think when you pull it up at the center by adding a foot to a 120-yard long rope that it's just enough to put your fingers under? How many people think you can crawl under, walk under, drive a truck under? Okay, that's probably the one that got the least number of votes, or maybe the first one. But it turns out, in fact, indeed, you can drive a truck under. Really? What? It's actually going to be about 13 feet high. And how would you calculate it? Well, it's just a consequence of what? It's just a consequence of the Pythagorean theorem, and you can just calculate it at home and see what happens. So we can thank Pythagoras for this. Yeah, and of course, if you want a little bit of intuition, here's a little bit of intuition. Some of you still have incredulous looks on your face. Here's a little bit of intuition. Here's my rope at the center. Here's the center of the field. Here's the rope, and I'm going to lift up this end, yes? Suppose I add just an inch to my arm. How far will I have to raise this rope to get an inch? Several inches, yes? Right? And of course, if you use the Pythagorean theorem, which says that the sum of the squares of the two short sides of a triangle equals the square of the long side, you can check this out. Pretty nifty. Did you like that trick? How many people like that trick? Yes? Awesome. That's a fun fact. Okay, while we're on the topic of Pythagorean theorem, this is of course, very, very old theorem. Dates back to antiquity. Pythagoras was perhaps the first known proof. Although that's another thing about some of these really old facts, is that many of them were discovered independently by many groups of people. And of course, we are living here in the West, and we're often influenced. I mean, we tend to know the things that the cultures that we're part of, but it's quite likely this is discovered in many other contexts. But the first thing we know about is Pythagoras, Pythagorean proof. Let me show you, but there are many proofs, and let me show you just a couple of proofs of the Pythagorean theorem because they're cool. One of them was actually proved by somebody who's not professionally a mathematician. And this was one of our former presidents. James Garfield came up with this proof. Okay? Which goes to show you that people can do math for fun, right? And it's a very simple proof, and it basically what Garfield did is he drew, if you have a right triangle, and the two side lengths are C. So these are the green triangles. They're the same right triangle. They're just oriented so that if one side's called A, you can't see that, but I'll write it here, and one side's called B, we'll put them down so that one of them has A on the bottom and one of them has B on the bottom, yes? Okay, and then you form the yellow triangle, okay, and that's basically got two side lengths C, okay? All right, so this is what Garfield's argument was. This is kind of nifty. Garfield said, hey, let's just use the formula for the area of a trapezoid. Now, of course, who knows the formula for the area of a trapezoid? Well, our president did, right? Okay. And it's not hard to actually to guess what it is, Right? How many people here know the formula for the area of a rectangle? Yes, height times width, right? Well, would you agree that if I just lengthen one of the ends and shorten one of the ends, that the thing would have the same area? So basically, if I take the left height and the right height and average them, a rectangle with that height and the same width would have the same area. So that's what we'll do. What's the average of A and B? Well, this whole thing is area of the trapezoid is 1/2 A plus B. That's the average of the two heights times the width. And what's the width here? A plus B. Right? Oh, okay, great. So the area of the trapezoid, if I calculate this, is just 1/2, some more algebra, A squared plus 2AB plus B squared. Correct me if I do something stupid. Okay, great. That's the area of the trapezoid. Okay, now, what's the area of the triangles? Well, the area of the triangles, this is 1/2 AB, and this is 1/2 AB, yes? Right? Okay, great. So here's a question then. What is the area of the yellow triangle? Well, it's just the whole area minus the green area. Yes? So if I take this expression and I subtract the green area, would you agree I'm taking this expression and subtracting AB? Because a half plus a half AB is AB, yes? Oh, okay, great. So the area of this piece, this final piece, is simply, this is 1/2 A squared plus B squared, because I'm subtracted off this portion here with this portion here. Yes? Oh, but what is another way to calculate the area of the triangle with two side lengths C that's right? Well, that's just also equivalently 1/2 C squared. So A squared plus B squared equals C squared if you just multiply everything by 2. Okay. Pretty nifty. How many people liked that proof? Liked Garfield's proof? Yeah, good. Okay, some of you liked it. Okay, now, this is not my favorite proof, but it's kind of nifty because it shows that even politicians can do math, which you might not know today, but okay, no, sorry, I'll just stop with ragging on. Okay, great. Let me show you what I consider to be my favorite proof, my favorite Pythagorean proof. And this one's going to go by really quickly. So here's the idea. So of course we're looking at a triangle like this, and I think we agree that what I'm trying to verify is that the area of this, which is A squared, plus the area of this, which is B squared, is the same as the area of this, which is C squared. Right? Would everybody agree with that if the side lengths are A, B, and C? Okay. Now, wouldn't you agree if I'm trying to show that A squared plus B squared equals C squared, that it's equivalent to multiplying both sides by some constant, right? I mean, you can't stop me from multiplying both sides by the same thing. Would you agree that if one is true, the other is true? So it's enough for me to show that a multiple of A squared plus B squared equals a multiple of C squared, yes? You with me on this? Oh, but the multiple K is just a scaling, right? So I could change, I don't have to be looking at squares, I could change the thing I'm looking at. So for instance, instead of showing the sum of the areas of the two smaller squares is the area of the bigger square, I could instead take some other object like, oh, I don't know, I could take a smiley face, right? And I could show that the area of that smiley face is the sum of the areas of these two smiley faces. Right? If I wanted to, right? I could put any figure there I want. Okay, good. So if you buy that, well, I'm not going to put that figure then. Here's the figure I'm actually going to use. I will take my original triangle, and instead of using a smiley face or a square, I will show you that if I take a copy of the original triangle, a similar triangle, it's actually the same triangle there, and put a copy of the triangle on every side, a similar triangle on every side. This is not exactly the same thing, but there's a copy of the triangle. Oops. Try again. This has got to be similar, okay? And then here's another one. Okay, those are basically similar copies of the triangle are on all three sides. Yes? All I have to verify is the sum of the areas of the two small triangles is the same as the area of the big triangle. Yes? So here's how I'll do it. It's very simple. All I'll do is draw up an altitude so that I have cut the green triangle to two pieces, and then I'm just going to fold over this triangle and fold over this triangle, and you see they actually completely match when they fold over. And they match to the same size as the triangle on the other side, because that's just the big thing. If you fold this over, oops, if you fold this over, it'll cover the whole thing. So the sum of those two triangles actually is the bigger triangle area. Okay, cool. How many people thought that was cool? Okay, you don't have to say that just to make me happy, but I think it's pretty nifty. Okay, great. Let's move on. Ooh, did you know that there is in fact a spherical Pythagorean theorem? Spherical Pythagorean theorem. Really? What does it mean to be a spherical Pythagorean theorem? Anybody have any ideas? We should be looking at what? Triangles, yes. Where? On a sphere. And one of the angles in the triangle better be a right triangle. So let's draw a picture. Now, you pick 3 points on a sphere. Now, the sides can't be straight, so they're going to be a little curved. But you're just drawing the shortest path between 2 points on the sphere. And they're going to be slightly curved, yes? And to talk about an angle being right, you mean that basically if you look really close at a corner, it's going to have a right angle. Yes? Everybody with me? Now the weird thing about spherical triangles is that the sum of the angles don't necessarily add up to 180. In fact, you could have a triangle where all the angles are right. Right? Like take the North Pole, go down to the equator, move over 90 degrees, and then come back up to the North Pole. All the angles there will be right. But when we talk about right, just pick one of them that happens to be 90 degrees, and I will call the two sides next to the right triangle A and B, and the third side C. And now the question is, what's the relationship between A, B, and C? And so here's a relationship, it turns out. It turns out that the cosine of C equals the cosine of A times the cosine of B. I have to be really careful here. This is for a unit sphere, that is a sphere of radius 1. Or if you don't like that, if you don't want to deal with a sphere of unit radius 1, this is for the case where if I have a sphere of radius r, I divide all these things by r. Okay? So this is radius r. Interesting. This is the spherical Pythagorean theorem. It doesn't look anything like the regular the Pythagorean theorem, does it? Does it? Well, in fact, it actually is. So this is kind of nifty. This is quite nifty. And let me show you why. This is really cool. So how many people have here had a little calculus? Just a little bit of calculus? Awesome. Okay. Well, so check out what happens here. The first thing to notice is, would you agree that if my sphere got really big, radius gets big, this thing gets flatter and flatter and flatter, yes? And so that triangle, this formula should change into the regular Pythagorean theorem if r goes to infinity, yes? Oh, okay. But if r goes to infinity, what's c over r doing? if r goes to infinity? C over r is going to something really, really tiny, yes? Okay. And if you take the cosine of something really, really tiny, then what do you get? Very good, you get 1. But well, so if that's true, then 1 equals 1 times 1, and we knew that already. So let's do take a little finer approximation. Cosine of something really, really tiny equals 1 plus another term, minus another term. Think Taylor series. Cosine of x is 1 minus, what's the next term of the Taylor series? Well, if you calculate it, it's x squared over 2, it turns out. Okay? Oh, really? So if I take the next term in the Taylor series, this thing just becomes 1 minus approximately c squared over 2r squared. And we're saying that's equivalent to approximately 1 minus a squared over 2r squared times 1 minus b squared over 2r squared. And when all is said and done, if you start canceling things and ignoring things, which is what we often do when we work with approximations, you'll find that c squared is approximately a squared plus b squared, and voila, the regular Pythagorean theorem. Ah, nifty. Who do we have to thank for this? Well, it turns out that we have a lot of astronomers who love mathematics. A lot of astronomers, both in the Greek and Islamic world. Astronomers to thank for the origins of the spherical Pythagorean theorem. You can find evidence of this in their writings. Cool. How many people like that? Is that cool? You like that? Awesome. Great. Here's a fun fact I really love. I love this fun fact. This is so awesome. So here's a question for you. If I take a number like the square root of 2 and I square it, what do I get? 2. Okay. Oh, interesting. So it's possible to take an irrational number and raise it to a rational power and get something rational. Yes? Rational means written as a fraction. Okay, so here's a question. Is it possible to take something irrational and raise it to an irrational and get something rational? Is that possible? How many people think no? How many people think yes? Okay. Well, let me prove a theorem for you, which just means let me show you why it's true. Theorem, yes, it can be done. That's a great theorem. Just say yes. Okay, here's an argument. This is one thing that's really clever. What's fun about this fact is not the result necessarily, but how you prove this result. Because what's going to happen is we're going to show that this is true without showing you a specific example of why it's true. What? It's completely non-constructive. And this is how it goes. This is really great. This is awesome. So here we go. So here's a question. Let's look at. How about, let's just do the square root of 2 to the square root of 2. Is it rational? Well, I don't know. But if it is, if yes, we're done. We found an irrational to an irrational that's rational, correct? Yes? So what's the other possibility? If no, then the square root of 2 to the square root of 2 is irrational. Would you agree with that? Okay. So you can't stop me from raising it to an irrational power. And what I get is the square root of 2 to the square root of 2 times the square root of 2, otherwise known as 2, and that's 2, and we're done. How many people like that? That's awesome. Nifty. So either way, we know it's true, but we don't know whether root 2 to the root 2 actually is rational. Actually, some people do. And what do you think the answer is? It turns out to be irrational. Turns out to be irrational. Who do we have to thank for this? I have no idea. This is one of those things that's passed down, folklore, and people just go ooh and ah, and they share it. It's kind of like sharing a joke on Twitter that you didn't write. Okay. Oh, I love this one. This one's great. This one's awesome. If you have a piece of paper, you can do this. Draw a triangle, any triangle. Just make sure it's not special. Like, make sure it's not a right triangle, for instance. Oh, that looks right. Ugh. It's actually really hard to draw something very general, but I'm going to try. Okay, here we go. Here's a triangle, and I'm going to ask you to mark 9 special points on this triangle, related to this triangle. Okay? If you want to do this on your own sheet of paper, you can. What I'll do is I'll ask you to mark the midpoints of each side. Yes? That's one set of points. Midpoints of every side. Okay, great. Now the next thing I'm going to ask you to do is to drop an altitude from each corner to the opposite side. But what that means is pretend that one side is the floor, drop something from the corner and see where it lands. Are you with me? So that's one, it's going to be a right angle in this case. Now if I imagine this side being the floor and I drop something from it, it'll actually go to there approximately, yes? And if I drop something to that side from the other side, it'll actually go here. And it's actually a fact that all these altitudes cross somewhere. They will cross, they cross somewhere, which is not a point I'm interested in right now. But they happen to cross. The 3 points I want you to mark, though, are these points. The points where they land on the other side. So here's 3 more points. Are you with me? That's 6 points. Okay, now look at where the altitudes all cross. That's called the orthocenter, by the way. Where those cross, and look at the point that's halfway between the orthocenter and the 3 corners. So in this case, this point, the point where they all cross, halfway to each of the 3 sides is this point. There's one here, there's one here, and there's one here. Those are 9 points. And if you've done this right, if your things to scale, by the time you're done, those 9 points all will lie on a perfect circle. Oh, really? This is called the 9-point circle. And for that, we have to thank a German mathematician, Feuerbach. Feuerbach 9-point circle, and this is early 1800s, 1822 or so. Ah, nifty. Now I know some of you drew an acute triangle or an obtuse triangle. It still works. You just have to extend the edges. The altitudes may not fall inside the triangle. They'll fall outside the triangle. Okay, but it still works. It's nifty. All right, how many people like this one? You like this one? Awesome. Great. Great. We're on our way. Oh, this one's a great one. I love this one because it's all about friendship. This is awesome. This is called the friendship theorem. Friendship theorem says this. Suppose you go to a party. And at the party, suppose it's the case that every 2 people have exactly 1 friend in common. Okay? Every 2 people have exactly 1 friend in common. Then something amazing is true. If this is true, then, can you read that? Oh, yeah. Then it turns out that there will be 1 person who is friends with everybody. Oh, yeah, really? Yeah, so if you go to a party where any 2 people have exactly 1 friend in common, there's 1 person who actually is friends with everybody. And in fact, what we know a little bit more, it turns out that the graph of connections between people basically looks like a bunch of triangles that are connected at it looks like this. This is what the connections must look like. It must look like this. A bunch of triangles connected at a point. That's basically the way it must look. And that person in the center is friends with everybody. Now, does this have any practical application? Well, I don't know. I mean, go to a party and start asking people who they know. That might be kind of creepy. Okay, but who do we have to thank for this? These are several famous combinatorialists. Paul Erdős, some of you may have heard of, one of the most prolific mathematicians, and people like to count how many paper connections they have with Paul Erdős. How many people have heard of an Erdős number? Okay, that's Paul Erdős. And Alfred Renyi is Hungarian, and Vera Soch is Hungarian. If any of you have gone to Budapest, you have an opportunity. I had a student once studied with Vera Soch, and they've got a great set of combinatorialists there who prove lots of really cool theorems. The friendship theorem. Awesome, great. Okay, let's do a few more here. So here's a fun fact. If you take a bunch of cubes, the cube of 1 plus 2 plus 3 plus all the cubes, 1 cube plus 2 cubes, 3 cubes, 4. Let's count that, actually. Can we do that? What is 4 cubed? 64. And what's 3 cubed? And what's 64 plus 27? 91, right? Plus 8. 99. Plus 1. 100. Really? Oh, that's interesting. If I just add 1 cubed plus 2 cubed, what do I get? 9. Oh. 100, 9. What if I add 1 cubed, 3 cubed? 27 plus 9 is 36. Something funny going on? 9, 36, 100. Those seem really special. In fact, what are they? They're all squares. And in fact, the sum of cubes, in this case, turns out to be the sum of the numbers squared. 10 squared is 100. Yeah, right? 6 squared is 36, and 3 squared is 9. So this is a cool fact. It's true in general, okay? And if you want, you can prove it by induction, those of you who know what induction is. And of course, we have a couple of people to thank here, and the reason I said we can thank them is because, well, first of all, our Aryabhata is one of the first mentions of this, of noting this, but Al-Kharajhi is probably the first person to prove it. And what Al-Kharajhi is also known for is for developing the method of induction. Okay, this is another Persian mathematician. Okay, but I'm going to show you a completely different proof, which isn't induction. It's just it's a proof by picture, and this is cool enough for me to do. Okay, so here we go. I am going to. Would you agree that if I want to do this, let's see. Would you agree that this 1 cubed is just the volume of a little cube of side length 1? Okay. And 2 cubed is just the volume of a cube of side length 2, yes? Yeah? And 3 cubed, okay, you get the picture. All right, now, just wait, this is so awesome. Look. Okay, I feel compelled to do one more. Is that okay? Yes. Okay. Perfect. Okay, now, check this out. I'm going to show you why if you stack all these cubes in a different way, you'll see the right-hand side is the same. Why? I'll just put everything in one layer, and I'll just show you the top. So there's the first cube, but I'm showing you just the top. Well, if I want, I can break up the blue 2 by 2 into a 2 by 1, a 2 by 1. That's the first layer of 4 squares, yes, in each layer. And the second layer goes right here. And would you agree this is 1 plus 2 squared? And if I want to do 1 plus 2 cubed, I can just, well, I got to show you why 1 plus 2 plus 3 squared is the same, yes? So you can't stop me from adding 3 more squares on each side, and then filling out the rest with a 2 by 1, a 3 by 3 by 2, and a 2 by 3, and a 3 by 3. This, my friends, is layer 1, which I'll label A. This is layer 2, which I'll label B. I'll have to use one of these together with one of these. And then C will be the third layer. Yeah? That's 1 plus 2 plus 3 squared on that side, right? And now you can see what's going to happen in the last case. I'll just draw this out. Just one more thing, and if you like it, you can clap at the end. There we go. 2 by 4, 3 by 4, 4 by 4, 4 by 3, 4 by 2, 4 by 1. And if you want to match these up, A, B, C, D, how am I going to do it? I'll call that A. I'll call that B, and I'll match B up with this one. I'll match C up with this one, and I'll match D up with this one. 1 plus 2 plus 3 plus 4 squared. Same number of squares. How many people like that? Awesome. Yeah, because you get insight from doing this, doing a picture proof. All right. I think we just have a couple more here. So here, how many people know what a magic square is? Yeah, a magic square. It's an array, a square, where you fill in numbers such that every row, column, and 2 diagonals add up to what? The same number, whatever it is. Okay. So here's an example of a magic square. Here's one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, cool. How did you do that? That's so awesome. Well, I used a special trick. I won't tell you what that trick is, though. But this is a magic square size 3, and every row, column, diagonal adds up to 15. Okay. Now, magic squares have been around a long time, celebrated, studied in many cultures: China, Persia, some of in Europe, and even in Africa. And the reason we know this is that we have the writings of Muhammad ibn Muhammad from an area that's now Nigeria. It wasn't at the time. And he came up with a construction, a very interesting construction for doing a magic square. And I'll show you what his construction does in the case of a 5 by 5. There are other methods. I just want to show you this one because it's kind of nifty. So here's what he said, basically. The rule is the following. You start in, actually doesn't matter, but we'll start in the upper right square. And then we're going to we'll do knight's moves, all in the same direction. So if I go 1 and then I go down to 2, that's a knight's moves on a board, chessboard, right? And then I'll go down to 3, yes? And now what I have to imagine is this board wraps around. So if I leave the bottom, I enter the top, and leave the side, enter the other side, yes? And so I'll keep going as far as I can. And let's see, if I go down, let's make sure I'm doing this right. This is 4, I believe, yes? Down and over, down, over, left 1, down 2, yes? Left 1, down 2. Now, what happens here with 5? Uh-oh. I can't go down to the next one because 1's already filled, yes? So what he says is then you do a special rule. You move over 2 units and put 6 there, yes? And then you just continue. 6 goes down to 7, which is here. Oops, wrong. 7. 7 goes down to 8, etc. And just keep going. And every time you just remember the rule, if you can't keep going, move over 2. The nice thing about this rule is it produces a magic square, not only with all the rows and columns and both diagonals that add up to the same number, but all the diagonals with wraparound add up to the same number. Kind of nifty. Really neat contribution from an African mathematician. And if that wasn't enough, magic squares are so awesome. Here's another thing that was only recently noted about magic squares. 3 by 3 magic squares. So if I look at 3 by 3 magic squares, check this out. Something that's really nifty is if you take this magic square and you just pretend that the first row is a number, like 816, and square it. Why would you do that? Well, because something amazing happens. If you read the rows as numbers and square them, guess what? What happens when you sum up these squares? You get 1,035,369. Yay! Is that fun? How do people think that's fun? Okay, maybe that's not fun, but if you now take the rows and read them backwards as a number, 618 squared plus 753 squared plus 294 squared, and you sum them, guess what you get? Whoa. Say whoa if you didn't expect that. Whoa. Okay, great. But that's not all. Guess what? If you read the columns as numbers and square them and sum them one way, and read them backwards up the columns, sum them, square them one way, you actually get the same number, but not the same number as this one. In other words, the same property holds reading the columns. It holds for the diagonals. It's kind of an amazing fact. Probably the first place that I know of it was noted was in a Martin Gardner book. But an undergraduate actually asked the question, is this true for all 3x3s? And this undergraduate at Harvey Mudd actually proved that it actually holds for all 3x3 magic squares. You just have to interpret, if you have more than one digit, you have to carry. So if that middle number were an 11 instead of a 1, the first row would be read as 916. And in reverse, it would be read as 718. Okay, before I do my final fun fact, I just want to point out another fun fact, which is this year, what's sort of the Nobel Prize in Mathematics went to 4 mathematicians, and it was the first time we actually awarded a Nobel Prize to a woman, first time to a mathematician from Latin America, and the first time to an Indian mathematician. And the reason this is significant is if you think a little bit about the history of scholarship, not just mathematics, but scholarship in general, there have been many groups for which it's been hard for those groups to be able to study or to have an education, right? Some of the early women mathematicians actually had to take extraordinary lengths to actually get educated, right? So women weren't admitted into universities at one point. And some of the famous women mathematicians actually started off by using pseudonyms in their correspondence. So Sophie Germain did that with Gauss, just because of the fear that they would not be received. And so, of course, we've come a long way, but it's taken a long time for us to actually start recognizing the work of diverse groups of mathematicians. And of course, we hope this trend continues. All right, last trick. The last fun fact is a trick. It's a card trick. And to do that, I'm going to switch to the document camera. This is really cool. It's one of my favorite card tricks. So here's a deck, yes? Looks like an ordinary deck. Mixed, but of course, you don't believe me, so I'm going to have somebody shuffle the deck. Who here can shuffle the deck? A riffle shuffle. Somebody do a riffle shuffle? Okay, you're a little hard to reach, but can one of you riffle shuffle? No. Okay. You can riffle shuffle. Okay, good. So I'm going to give him the deck. Just give it one shuffle. You don't need to give it a flourish. Just shuffle it in. Yeah, very good. Thank you very much. All right.
I think it's a new combination.
Yeah, that's right. He just made history. Oh, awesome. Okay. So, is there any possible way after he shuffled the deck that I could know the ordering of this deck? No, I wasn't in cahoots with him. I'll pay you later. So would you believe then that I was born with an amazing ability? No? Amazing ability to feel the colors of the cards with my hands. Now, it's actually not a very refined ability. I can't tell you what color this card is. But I can pull them off the deck in pairs. Red, black, opposite colors. Okay? And so just to, so you can see that, Red, black, yes? Red, black. Red, black. Red, black. Now, of course, if I'm just doing this by randomly, then the chances that I'm doing this is actually about 1 in 2 for each pair. And as soon as I do more than 8 of them, it's 1 in 500, 512 to be exact, yes? 1 in 1,024 chance that I got all those to be pairs of red, black, yes? And if you like, I could keep going. Or you could just believe me, I have an amazing ability. Yeah? And we could all go home. No? No? Okay, well, a magician never reveals his secrets, but I'm not a magician, so I will. This is so awesome, because this is a trick. It's a mathematical card trick, so you don't actually you don't have to worry about, it's not sleight of hand. You're not going to mess it up if you just remember the rules, it'll work. This is so awesome. Let me show you. Okay, so clearly I stacked the deck beforehand, yes? Yes? Okay, but I had to do so in such a way that no matter how he shuffled, I would still know something about the deck. And this brings up another lesson from mathematics, because math is the science of patterns after all. And what we're trying to do is understand patterns that remain after a riffle shuffle, yes? It turns out we know that a riffle shuffle is not enough to mix the deck. In fact, it was proved in the early 90s that it takes 7 shuffles to mix a deck well of 52 cards. That was proved by Percy Diaconis. And so there is something that happens after one shuffle. There's still order. And so here's what I did. Before the trick started, I actually stacked the deck in a special way. I stacked them, so that they're alternating red, black, red, black, red, black. And this one actually still is quite ordered like that. Okay, no, it's not. But I stacked them red, black. I'll just do a few here, yes? Okay, so that's what I did. Now, of course, when you show people at the beginning, they won't notice it because the cards clump, right? You should show them that it looks mixed. Then you invite somebody to shuffle, yes? Now, this is the only part you have to remember. If you forget this, the trick won't work, or may not work, okay? When you hand the deck to your friend to shuffle, you have to cut the deck. You have to remember to cut the deck so the colors on the bottom are different colors. Are you with me? If you remember that, then the trick will work no matter how he riffle shuffles. And I advise you, when you ask him to riffle shuffle it, to make sure you tell him to shuffle it once, because if they start shuffling it more than once, you're in trouble, okay? Or you should have another deck prepared, as I did. Okay, so remind me your name again? John. So John is going to drop cards, yes? But how is he going to drop them? I don't know. They'll fall off either one side or the other, right? Yes? So let's watch underneath what's happening when he drops cards from either side of the deck. So which of these two sides is going to fall first? I don't know. I'm not sure. Maybe it falls from this side. But if it falls from this side, what color must the next card be, no matter which side it falls from? Red. So the next one will be red, even if it falls from the same side. Now, what happens when that falls? What's the two colors? Black, red, and we're back to where we started. Which side's it going to fall from now? I don't know, maybe red. But what's the next card have to be? Black. And so no matter how he shuffles, even if he starts falling a lot from the same side, or if it alternates, it will be, it'll come off. Now, it won't be red-black anymore. Do you see here? It's not red-black anymore. But every pair, starting from the top, is going to be a red-black pair. Yes? And then the only thing you have to do to make sure people are confused about it is you don't show. Good save. You don't show them what you're doing. You fish around to make it sound like you're picking cards randomly, but you're just picking them off the top. 2 by 2 by 2. Anyways, I hope you enjoyed that, and have a good night.